Okay, so we're just going to revisit titration. You've learned about titration in Chem 1A, and you did some of it in Chem 1B, but now we're going to just kind of go over some of the finer points. So, just an overview, titration is just a technique, a procedure in which increments of a known reagent called the titrant are added to the analyte, the thing you're analyzing, until the reaction between the analyte and the titrant is complete. So as you're adding, and we have I have an illustration here from Harris. You've got a burette here with your titrant. Your analyte's in here. This is more the 1B version because we let you use the magnetic stir bars now. And we're adding the titrant. So as we add titrant, we need it to react very quickly with the analyte and to react completely. And so we'll keep adding this until this reaction is finished. There are different types of titrations. You're probably most familiar with acid-base titrations, where you've got typically sodium hydroxide in the burette and you're analyzing your unknown weak acid or something. You can also have oxidation reduction titrations. Those involve redox reactions. You can have complex formation and precipitation reactions as the basis of titrations. So there are two important points in a titration, the equivalence point and the end point. And ideally these would be the same, but in practice they're not exactly the same. So it's important to understand the difference. The equivalence point is when you've added a stoichiometric amount of titrant. So you've added just the right amount to react with your analyte. Unfortunately, that is very difficult to detect because it doesn't like jump up and down and say, hey, we're done. So the end point is what we actually measure. So there's a difference, and the difference between the equivalence point and the end point is known as the titration error, and it's pretty much unavoidable. So the best we can do is to minimize that titration error, narrow the gap between those 2 points. We can do this by choosing an appropriate indicator. The indicator in a pH titration needs to change color in the right pH range. We can also estimate what that titration error is using a blank titration, where you titrate a solution that's similar to your analyte solution except without the analyte, and you see how much of the titrant is needed to give you a result. It's usually going to be quite small, but by doing a blank titration, you can then subtract that amount from your volumes and you can get a more accurate result. Any questions? So how do you determine the endpoint? You can do this by detecting a color change in an indicator. So indicators are compounds with physical properties that change in response to disappearance of the analyte or appearance of excess titrant. Oftentimes this is a color change. That's easiest to detect without any electronic equipment. For an acid-base titration, hopefully you remember drawing those pH curves. You can look at the curve of the titration, and that place where the pH is changing most steeply, that's where you want your indicator transition to occur at that pH. And so if you can get those two overlap as much as possible, that can be very helpful. Some problems with this, I'll point out later. How much of a color change? Is it, you've probably asked yourself or asked your instructor, is this pink? Right? Because you want to get just barely there, but then sometimes you're not sure because it's such a slight color change, and so that can be an issue. So another way to monitor the endpoint is using electrodes and monitoring a sudden change in either the voltage or the current. So this could be some sort of a redox or electrochemical titration, but it could also and would also include using a pH electrode to determine the endpoint. So you did an experiment like this in Chem 1B with the unknown weak acid, where you had your unknown acid in a flask, well actually in a beaker, and you added the sodium hydroxide in small increments and you recorded the pH. And then when you got closer to the endpoint, you added it in smaller increments and recorded the pH. And so you were able to generate on the computer this whole pH curve. So using an electrode like that, you're actually going past the endpoint, but you're looking at the data that you've collected to determine at what volume was that at the endpoint. And that can be more accurate in some situations than just trying to stop at the endpoint by a color change. You can also use change in absorbance of light by some species in the reaction. This might be the reactant of the analyte. It might be the analyte. It could be the titrant, or it could be something else that you've put into the solution to act as an indicator, but you're detecting the change using spectrophotometry of some kind. Any questions? So how well we can report our result of the analyte concentration is going to depend on knowing the amount of one of the reactants. We need to know what the concentration and the volume of our titrant is. So we need to make use of a primary standard. A primary standard is pure enough that we can just weigh it out and use it directly. You can find the mass, you put it in a known volume, and you know what the number of moles are. Primary standard. These are very pure, generally better than 99.9% pure. Another important thing is that they need to be stable under normal storage conditions. So this is something that you can have in the stockroom, and it's going to last at least months, if not years, just sitting there on the shelf. So that rules out a lot of things. It's also important that it be able to be dried. It could be dried by heat. I don't know if you remember, we dried our KHP in the oven for Chem 1B. Or a vacuum can be used to dry it, and that's important because almost any substance can absorb a little bit of moisture from the air, and that's going to affect its mass, and that's going to affect the number of moles that you think you have. So that can affect your ultimate result. So examples of primary standards include KHP, potassium hydrogen phthalate, oxalic acid dihydrate, and sodium carbonate. So I'm going to stop asking if you have any questions, and if you have questions, you just need to get my attention somehow. So usually the titrant that you need is not available as a primary standard. So sodium hydroxide is convenient and inexpensive, but it's not available as a primary standard. Because even if, you could make very pure sodium hydroxide, but it's very hygroscopic, meaning it absorbs moisture from the air very quickly. It's sold in pellets, and if you go to weigh the pellets out, you can almost watch them getting wet. And on the balance, you'll just see the mass just slowly goes up. Kind of like when you have an open beaker of water or acetone on there, and you can just watch the mass drop as it's evaporating, right? So there's no way you can have a primary standard for sodium hydroxide. And this is true of many of our titrants. So we standardize the titrant. Process of titrating a primary standard to determine the concentration of the titrant. So this is where you take your sodium hydroxide solution, that is, you know approximately the concentration, pretty close, and then you're going to titrate it with a primary standard so that you can calculate the molarity of your sodium hydroxide. Then you take the sodium hydroxide and you titrate your analyte.
So that's what we're doing in our mini project.
That's what you're doing in the mini project. Yep. Yep, that's exactly.
Are you sure?
Okay, that's what you're supposed to be doing in the mini project. So an example, titrating sodium hydroxide with KHP. The reason we do that is not to give you practice in doing more titrations. It's to find out what is the concentration of the sodium hydroxide. So another issue with sodium hydroxide is that as it stands, carbon dioxide from the air can dissolve in the solution, and that will react with the sodium hydroxide to form carbonates, like hydrogen carbonate ion, and that will affect the pH of the solution. It essentially changes the concentration of the sodium hydroxide. So once you've standardized the sodium hydroxide, it's considered a standard solution. With sodium hydroxide especially, unless you take some significant precautions, which is what we tried to do in Chem 1B. I'm not sure how successful that was, but we boiled the water to get all of the dissolved gases out. And then we made the solution with the boiled water and stored it in a plastic bottle, right? So in theory, we're keeping most of that carbon dioxide away, and so we could store it that way. You'd still only be able to use it as a standard solution for a matter of days, right? Because every time you open it, it's going to get some more air in there. So standard solutions like sodium hydroxide may be unstable, and they will need to be standardized with each use. That's true of the potassium permanganate as well that we did some redox. Do you remember the lab practical in Chem 1A with that beautiful purple stuff? We can make that and we can standardize it, but over time, its concentration will change. So you standardize it and then you use it. So there are two main types of titration, a direct titration and a back titration. So the direct titration is like the regular kind. You take your titrant and you're adding it to the analyte until you detect the endpoint. So this would be like something like using sodium hydroxide to titrate acetic acid. In a back titration, it's sort of backwards. What we do is we add a known excess of a reagent to the analyte. That reagent will react with the analyte, but there's excess, and so some of that reagent will be left. And then we titrate the excess with a third thing. Okay, so you've got your titrant and your analyte, and then you also have this reagent that's added in excess. So this can be useful, for instance, when the endpoint of the back titration is clearer, is easier to see than the endpoint of what would be a direct titration. Or you might use it when you need an excess of reagent for complete reaction. So an example from Chem 1A was the antacid titration, where we took the fake Tums, the generic Tums, and we wanted to find out how much calcium carbonate was in the tablet, right? Well, calcium carbonate reacts with hydrochloric acid, but calcium carbonate is not very soluble in water. And then the tablet has all kinds of other stuff in it as well. So that reaction would be very slow. And one of the things we need for a good titration is that the reaction is quick and complete. So instead of trying to mess around with that, what we do is we take a known amount of hydrochloric acid, add it to the tablet. For good measure, we cook it for a while. You don't do that for everything, but just to help it dissolve and make sure that the reaction is complete. So now that sodium hydroxide has neutralized, the calcium carbonate has neutralized some of the acid that was added, but there's some acid left. So we find out how much acid is left by titrating it with sodium hydroxide. So it's sort of a roundabout thing, but once you get a clear idea in your head, it's actually very clever. And I think that's one of the fun things about analytical chemistry is figuring out a way around the problem. It's like, well, I can't do this. What could I do to get around it and still get at that answer? And that can be pretty fun. It can be pretty frustrating too, but it could be fun. So there are some considerations when you are titrating, and I realized that I learned most of these things somewhere along the way in my education as an analytical chemist. I don't exactly remember where or when I learned them. And because it just is almost second nature to me, I sometimes forget to tell my students some of these things. And of course in Chem 1A, are they going to get those subtleties anyway? Maybe not. But you guys have done all of this before, and so here are some tips. So the burette needs to be clean. And how can you tell if it's clean? Well, obviously, you rinse it with DI water and it should look clean. But the real test is to fill it up with DI water, clamp it on a stand, and let the water just drain. Just be patient, let it drain out. Examine the walls of the burette. If the burette is clean, you shouldn't see any water droplets on the inside. None. It should just sheet and come out. The water should just sheet and run down. So if there are droplets adhering to the inside of the burette, that means there's something there that's causing the water to stick. And that's not good, because if you've got water droplets remaining behind, that's going to affect your volume, right? Because you think, according to the change in the meniscus level, that you've added a certain volume, but some of that titrant is still hanging out on the walls. So there are ways to clean a burette. You do not generally use a brush on the inside of a burette because we don't want to scratch it at all. There are a variety of different cleaning solutions that can be used that'll basically just dissolve off anything that's in there, and those are typically not safe sorts of solutions, and so we let the lab techs do that instead of letting the students do that. And Chem 1A, we want to make sure that liquid comes out of the burette, right? That the tip isn't all clogged up with dried sodium hydroxide. We're not going to worry about water drops. But as I'm walking around looking at the burettes, part of me is just cringing because it's wrong. It's just wrong. You want to make sure your stopcock is working properly. It needs to be tight enough that it's not going to leak, but it needs to be loose enough that you can turn it easily. And so there's a balance in the middle there. We have burettes with Teflon stopcocks, and so there's a nut, and you can adjust that. If the stopcock is giving you a lot of trouble, it could be that it's assembled incorrectly. There's a washer and an O-ring and a nut, and the washer needs to be against the glass. If the O-ring is against the glass, every time you rotate the stopcock, it will loosen or tighten the nut depending on what direction you're turning it. Extremely frustrating. There are other types of stopcocks. The older style is a ground glass stopcock. So that's going to look kind of like those glass stoppers in the volumetric flasks. It's been ground so that it fits perfectly inside of the burette. Ground glass stopcocks don't have a nut or anything to keep them from popping out. So that gives rise to another set of problems of exactly how you hold the burette. They are typically lubricated with a type of grease to facilitate them moving easily and not leaking. But if you need to know about those, you can learn about those later. After you make sure that your burette is clean, you need to condition the burette, rinsing it 3 times with titrant. This does not need to require a lot of titrant, 5-10 milliliters per rinse. But there's no good way to dry a burette. And so we don't even try. Analytical chemists are just okay with things being wet, right? We just need them to be clean and we'll deal with the wet. We don't want to use a freshly washed burette with water inside of it because you add your sodium hydroxide and there's water in there, you've changed the concentration. So we add the sodium hydroxide, we rinse it through the tip and along the barrel, we drain it out. Now what we have left, instead of being pure water, is somewhat diluted sodium hydroxide. So then when we do it again, we're left with less diluted sodium hydroxide. And we figure after 3 times, we'll call it good enough, okay? Just occurs to me that might be an interesting thing to test. What is the concentration after 1 rinse, 2 rinse, 3 rinses? Could be interesting. When you fill the burette, you want to make sure you don't have an air bubble in the tip. The air bubble itself is not necessarily a problem. The problem is if the air bubble comes out during your titration. So it's important to get rid of the air bubble. For most titrations, you do not want to start at 0. Starting at 0 can introduce bias into your analysis, especially if you are titrating something that has been measured by volume. So, the acetic acid in vinegar lab, pipetting 2 milliliters of this vinegar solution. Well, if you start at 0, you kind of know it should take the same amount every time, right? And so whether conscious or not, you end up trying to get the same number each time. And I've seen students who do get the same number each time. And then, how do you do standard deviation on that when you've got 4 numbers that are the same? It's kind of iffy, right? So what you want to do is you want to start somewhere below 0, and then you titrate, and you don't pay close attention to where the volume is. You look at the color, and you're going for that first pink color. That's going to give you a more realistic and a more accurate result. Because if your first one was off a little bit, and then you're matching up the rest, then they're all going to be off. Make sense? The one exception to this would be when you're doing a pH titration with a pH electrode, where you're recording the pH. There, I'd say it is best to start at 0, just because it's so much easier to keep track of the volumes added. And you don't have that same issue of bias, because you're just recording the pH at various volumes. When you're reading a burette, there are some errors that can be made. One of them is parallax. Have you guys heard of parallax? I remember being lectured about parallax in undergrad. So parallax is that effect where how you look at it, whether you're looking down or looking up or looking straight across, affects how you see the meniscus. So here's a photograph of a meniscus in a burette. And if you'll notice at the 1 milliliter markings, that line goes all the way around the burette. That's actually for a reason. So see how this line for the 15 lines up almost perfectly? That means I'm looking straight across. They are lining up with each other. This one isn't quite as good, but almost. And so this one's lining up. That tells me in this part, I'm looking straight across. Because this meniscus is in the middle of the burette. It's not at the edge. And so if you're looking down from above, you're going to get a difference, kind of like in this line here. If you're looking up from below, you're going to get difference in the other direction. And so that can cause a significant error in your results. You always want to look straight across And you can use those 1 milliliter lines to let you know if you're looking straight across. You know, technology exists, and so we might as well use it. It can be pretty fiddly to read a burette. If you take a picture of it, then you can look at it at your leisure, right? Although I will say, having taken that picture myself, that taking a picture of it is a bit fiddly too. Another thing is read the burette to plus or minus 0.01 milliliters. So anytime we read an analog instrument, we should read between the lines. And what that means is we're going to look at the smallest divisions of the markings. So this is 15 and 14, and each of these little lines represents 1/10 of a milliliter. So then there's no uncertainty in the tenths place. If we look at this meniscus, it's between the 15 and the 16, so it's 15 point something, right? This is 15.5, 15.4. It is very clearly between 15.3 and 15.4. There's no uncertainty when we say 15.3. We always want to include an estimated digit when we record measurements. And so we estimate the next decimal place. In this case, it's the hundredths place. And so you just kind of eyeball it, and you imagine 10 divisions in there. And, you know, you get two people measuring that, and they might give you different results. It's okay. It's uncertain. But there's information there, and so we should record it. A mistake that students often make is they just go to the nearest tenth. But if you call that 15.3, I'd say it's actually 15.36 maybe, then you are not measuring as precisely as you could. Does that make sense? Another thing we want to do is we want to make sure that our titrant concentration and our sample size match up. So what do I mean by that? We want to use a reasonable volume of our titrant. We don't want to have to refill the burette, so we don't want to use more than the burette holds, but we also don't want to just use, 2 or 3 milliliters. So because the larger the volume we measure, the smaller the percent error. So we want to use enough titrant, but we don't want to use too much. So it's a balancing act between your sample and your titrant concentration. Sometimes you can control how much of the sample you use, and when we give you an unknown in lab and tell you to do a rough run, some people have to use more, and some people have to use less, depending on how much of the analyte is in their sample. And so you can adjust that so that you use a reasonable amount. 15 to 20 is typically considered a reasonable amount in a 25 mil burette. If you find that you don't have enough of the titrant during a titration, you could fix that in one of two ways. You could either make a higher concentration for your titrant solution, or you could use a smaller sample size. Sometimes it's not possible to use a smaller sample size. Like that antacid tablet, there's a limit to what you can do if you're analyzing one tablet. So then you have to maybe use a higher concentration of the titrant. So let's look at the effect of titrant volume on percent error. So a good titration will have an error of 1 drop or less. A drop is about 1/20th of a milliliter, or 0.05 milliliters. So we could calculate the percent error for these titrations using different volumes of titrant. So what is percent error? What's a percent? The part over the whole times 100, right? So percent error is the error in the measurement. So the measurement is the whole thing. And the percent, I mean the part is how much different is our measurement from the true measurement. So that would normally take the form of looking at the absolute error divided by the true value, and there's lots of different words you can use, times 100 to make it a percent. Absolute error is typically your measured value minus the true value, and then you divide it by the true value. Well, so here what we have is a measured volume of 5 milliliters, and we'll assume that that's somewhat close to the true value, and our absolute error is this 1 drop volume. So for the 5 milliliters, we're going to look at 0.05 milliliters of error by 1 drop divided by the 5 milliliters times 100. I didn't bring my calculator, but someone conveniently left one here. I don't have to use my phone. So I'm getting 1%. So this is a 1% error caused by being 1 drop off on a 5 milliliter volume. So what about for 10 milliliters? Yeah, it's going to be 2, not 2%, 0.5%. 0.05 divided by 10.
Oh, yeah.
Yeah, I know.
Yeah.
So by using twice as much titrant there, now we've cut our percent error in half. What about 20 milliliters? So 0.25%. So the error caused by being 1 drop off in either direction in getting to your end point, if you're using 20 milliliters, is only going to be 0.25% error. If you're using a small volume like 5%, it's 1% error. So why is it better to have larger titrant volumes? Smaller percent error.
Yeah, that's a lot, though. 20 milliliters is a lot.
Well, it is, and
Especially when you only have a 25 milliliter burette.
well, with the 25 milliliter burette, what you want to do is you want to probably aim for 15 to 20 milliliters. You don't want to try to get 25 milliliters, because then if you go past, you're in trouble. Because then you have to refill the burette, and every time you measure, you've got some error. So you want to minimize the number of measurements. But using a larger titrant volume will give you less of an error. Now, one of the things that bothered me about some of our labs and the way they were written, they've actually been edited now, and you guys aren't benefiting from that, but people after you are. They've been edited to use larger titrant volumes, because really, is saving a few milliliters of sodium hydroxide worth it? Actually, no, it isn't. So the previous ones were asking you to use like 12 milliliters, really just wanting to get past the 10. So at least with significant figures, you'd have 4 significant figures. But if you look at it this way, it's actually much better to get closer to 20 milliliters. This sort of a issue is also something to consider when you're measuring your analyte. If it's a solid analyte and you're weighing out a sample, which would be better, 1.2 grams or 0.02 grams? Is it better to have a small amount or a large amount? It's better to have a larger amount, Because if you think of the analytical balance, when we don't have a prescribed precision given or an uncertainty, we can assume plus or minus 1 in the last decimal place. So if the analytical balance gives us 4 decimal places, we can assume that it has an uncertainty in that last decimal place of at least 0.0001, right? So if you were weighing out 1.2 grams or 0.012 grams, we could also calculate the percent error from that, right? So 0.0001 divided by 1.2. Now, granted, that's small. It's 0.0083%. But if we're weighing out a smaller volume, it's going to be more significant. Now it's 0.83%. So you've got a percent error just from the measurement, right? And you can minimize that by measuring out a larger sample. You've got trade-offs, though, of how much sample do you have, what size equipment do you have. You know, you get better precision if you were using a semi-truck full of this stuff, but then also would you have a balance that would measure that accurately? So, you know, you've got trade-offs. Any questions? So here's the fun calculation. This is a back titration. And we're going to work on this one together. So the first thing you should do, I'm just going to treat you like my 1A students. The first thing you should do when you try to solve a problem like this is read the whole thing all the way through. So a cyanide solution with a volume of 12.73 milliliters was titrated with 25 milliliters of nickel solution, that's excess nickel, to convert the cyanide into tetracyanonickelate 2. So that's that reaction. 4 cyanide ions combined with a nickel ion to make this complex ion. The excess nickel was then titrated with 10.15 milliliters of 0.01307 molar EDTA, ethylene diamine tetraacetic acid. That made a whole nother line on the slide, so I didn't. And that reaction is given here. So the nickel ion plus 1 EDTA ion will give us this complex. The nickel cyanide, the tetracyanonickelate 2, doesn't react with the EDTA, so we don't have to worry about that. And then we're told if 39.35 milliliters of EDTA were required to react with 30.10 milliliters of the original nickel solution, calculate the molarity of cyanide in the 12.73 milliliter cyanide sample. So this is an example of a back titration. Right? We're adding excess nickel to the cyanide so that we use up all of the cyanide. And then we're measuring the amount of nickel that didn't get used up by titrating it with EDTA. So what we need to find out is how much nickel was added and how much nickel was reacted with the EDTA. The difference is how much reacted with our analyte. Do you follow me on that? Yeah. So, see, could I draw a picture? It's hard to draw a picture of things like this. Well, no, I have plenty of things to draw pictures on. I can draw pictures on here. I just don't know what to draw is the problem. So we've got a solution Well, maybe let's try a beaker. So here's our beaker, because it's easier to draw than an Erlenmeyer flask. And it's got some cyanide in it. And we want to know what's the concentration of cyanide. So what we do is we add some nickel ion. We add more than enough nickel ion to react with all of the cyanide. So we need to find out how much nickel was added to that solution. And then we titrate the leftover. Well, actually, let's not call it. Let's just say leftover. We've got some leftover nickel ion. And we can measure the nickel ion by titrating it with EDTA. And what we're trying to find out is how much cyanide was there by subtracting the amount that's left over from the amount we added to start with. We can find out the amount that reacted. Is that making sense? So we have a couple of different things we need to calculate. The exact order that we do them in doesn't really matter. This one's especially tricky because reading up here, 25 milliliters of this nickel solution, what's the concentration of that nickel solution?
1. Well, I was going to do moles.
We need moles per liter, but it doesn't tell us what the molarity is.
Can you do it as a ratio? Like a 4-to-1 ratio?
Well, there is a 4-to-1 ratio, but we need to know in this 25 milliliters of solution how many moles of nickel are there. So that's hiding down here. Because how did they figure out what the concentration of the nickel solution was? They titrated it with EDTA. So down here it says 39.35 milliliters of EDTA were required to react with 30.10 milliliters of the original nickel solution. So that is what we need to calculate the concentration of the nickel solution. We can't figure out how much nickel was added unless we know the concentration. So we've got a couple pieces of information here. I like to use balanced chemical equations to organize information. The way this slide is set up, there's really not enough room to do that. Well, let's just squeeze it in there anyway. So 39.35 milliliters of the EDTA. And do we know the concentration of that EDTA? Yeah, it's given up here. 0.01307 molar. And then that reacted with 30.10 milliliters of nickel solution. So it can be tempting to use the dilution equation to solve this, and I even saw that used in the that tech handbook, which really just makes me angry. Let's not use that, okay? What this is stoichiometry. There's a chemical reaction occurring here. So I have a volume and a concentration for the EDTA. That means that I can find out how many moles of EDTA were used, right? Then I have a mole ratio here, which happens to be 1-to-1, so I can find out how many moles of nickel there were. And then if I divide by the volume of the nickel solution, I can get the molarity of the nickel solution. So really this is a variation of grams to moles to moles to grams, where we're starting with volume at the beginning, and then we're going to end up with a concentration. So sometimes it's hard to know, well, should I start with this number or with that number? The units of molarity are moles per liter. Anything, yeah, people forget that. There's just capital M's all over the place. Capital M is not another abbreviation for mole. It's mole per liter. Anything that has per in it can be used as a conversion factor, and probably should be. Here we've got milliliters that cannot be used as a conversion factor. So we'll start with that, 39.95 milliliters, and then it's very helpful to label that. What is it? Well, that's the EDTA. So I'm going to go volume to moles of EDTA. And so I'm going to use the molarity in here, 0.01307. And I want to write it out, moles per liter. Because if you put the capital M in there, your brain just skips over it. It's moles per liter. And so we're thinking about the units and we're like, oh, wait a minute, this is milliliters and that's liters. Have you been introduced to millimoles? Millimoles are great. So if I take this molarity and if I do the same thing to the numerator and the denominator, it's equivalent, right? So all I'm going to do is I'm going to put a milli on the top and a milli on the bottom. And now I don't have to convert my milliliters to liters. So milliliters cancel out. So this is moles now, millimoles of EDTA. And I'm trying to find the molarity of the nickel solution. So then I need to go from moles of EDTA to moles of nickel. And I want moles of nickel here. And moles of EDTA down here. Yeah, we can just leave it in millimoles. All we have to do is put a milli up there and a milli down there. It's all good. So millimoles of EDTA cancel millimoles of EDTA. So now I have millimoles of nickel. I'm trying to get molarity, moles per liter. So here I'm dividing by the volume. The volume was 30.10 milliliters. So I do the math there. There are several advantages to stringing this calculation all together in one calculation. You don't have to write down intermediate values. There's no opportunity for rounding errors in the middle. And you can see how everything goes together. So to do this in your calculator, start at the left and move to the right and just go times the top, divide by the bottom. I really should have put numbers in here. I got distracted by the millis. This is 1 millimole per 1 millimole. And that ratio is from the balanced chemical equation. So I've got 39.95 times 0.01307. I screwed that up. Yeah, I should have brought my own calculator.
0.017347.
Okay, say that again. 0.0.
17347.
Are we using 39.95 or 39.35?
That's an excellent question. I wrote it down wrong.
I use 0.99.
Oh, okay.
Yeah, so I wrote 3.5 here, and this is 3.5, but then over there, brain fart, I wrote with a 9.
Oh, no, that's okay. Either one's fine.
Well, no, we want to get it right. Otherwise, why are we even bothering to do it?
Okay, so
Yeah, so then that's going to change it.
yeah, it's what is it? 347 is that? It's actually 086.
173.38375 is what my calculator is giving me. But mostly the same. No?
No. I got 17086.
17086. Okay, I'm going to try it again. So it's very easy. I mean, aside from writing down the wrong number, it's very easy to get a key wrong on your calculator. So I recommend always doing it twice. And if you get two different numbers, go for best 2 out of 3. So I'm going to try this again. My good calculator will show me what I did, but this little sharp thing is not very sharp.
I used to have one of these. Did not help.
Yeah. So I was off and you were right. So that's good. 086528. Of course, that's a lot of digits, right? Remember significant figures? So what I recommend doing is keep track of how many sig figs this answer should have and then carry 2 extras. If you carry 2 extras, you don't have to even worry about rounding the second one. You can just write them down. So sig fig rules, we have 4 sig figs here and 4 here. Those are exact, and 4 here. So this result should have 4 significant figures. This leading 0 doesn't count. So the 1708, that's my last significant figure. And so if I'm writing this down to use it, I'm going to keep the 6 and the 5. And I don't need to go any further than that. So the units on that are millimoles per milliliter. If we want moles per liter, just cancel the m's. Cancel the millis, right? That's all we need to do. So that's the molarity of that nickel solution. This is not the only way to do a calculation like this. But if you learn how to write it out like this, then you can see it in your head even when you don't write it out. And when you need to be extra sure that you got it right, or if you are working in a lab and making up a solution, they want you to write everything down. Because we had an incident happen where a solution was made incorrectly. So the stockroom person made a mistake, but the person had documented what they wrote down, and so we were able to look at the calculation and realize that the molar mass for carbon was used instead of the molar mass for calcium, which means that the solution was completely the wrong concentration and the experiment didn't work. But we knew why, and so that's a good thing, because then you can fix it, right? So then we have to remind ourselves, where are we going with this? What are we trying to do? So that's the molarity of that nickel solution. These are the 2 things we need to find: the amount of nickel that was added and the amount of nickel that's left over. So the amount of nickel added was 25 milliliters of this solution, right? So 25 milliliters times 0.0170865. It would be most convenient to leave that in millimoles per milliliter. Right? The milliliters cancel out. So what'd you get? 0.13?
For this?
No, yeah, for this.
0.427.
Yeah, that's what I got. 0.427. How many significant figures should the result here have? 4. Because 25.00, 4 sig figs, and this had 4 sig figs. We just have a couple extras carrying along. So I look at my calculator, 4.4271. That's my last significant figure, and I just write down the next 2 digits. And so it's that many millimoles of nickel. So that's how many millimoles of nickel were added. 0.427163 millimoles. We're getting closer. So then, how much was left over? Where do we what number do we need to figure that out?
You just subtract the two.
Well, what are we going to subtract?
The millimoles and
We only have one quantity. We need to subtract the leftover nickel, but we first need to find out how much nickel was left over.
so we could do that by taking the millimoles of nickel that we've just found, the 0.4271, subtract it from the 0.017.
No.
You have to use the second reaction, right?
We're going to use this reaction, nickel and EDTA, but it's this sentence here. The excess nickel was titrated with 10.15 milliliters. Okay, so this is what we need to find how much was left over. There's a lot of words, a lot of formulas, a lot of numbers in this problem. And that's why I thought it would be good to kind of talk through it in case I gave you something like this on an exam, then you could figure it out. So how are we going to go about calculating millimoles of nickel from that? Think grams to moles to moles to grams, but milliliters to moles to moles.
So the 0.427, that was how much was added to the cyanide solution? So then,
Yeah, this is the amount that was added,
yeah, and then,
and the excess was titrated
so then
and
you-
took this much.
You multiply the 10.15 times the molarity of EDTA,
Mm-hmm.
and you do the stoichiometric conversion to get the moles of
Yep.
nickel that was left.
So 10.15 milliliters of that EDTA solution, 0.01307 millimoles per milliliter, so the units cancel out. That's millimoles of EDTA. We want millimoles of nickel. It's 1 to 1. 1 millimole of nickel to 1 millimole of EDTA. And so the millimoles cancel out. So 10.15 times 1307. I got 0.132660. So I'm using you guys as my second calculation. So that's the amount that was left over. So that's the leftover amount. You can write that up here. 0.132660 millimoles. So I've got the amount added and the amount left over.
Subtract.
So I subtract and I find the millimoles used. I'll put a minus here. And I'll put the answer over here because I didn't plan this out very well. 0.427163 minus 0.13266. 0.294 503. That's the amount of nickel that reacted with cyanide. If we were doing a direct titration, we'd have, it would be a volume and a concentration, but we'd be getting this number directly instead of having to go around the back way. Are we done? No, we're not done. So we got that 0.29450. So okay, help me out. 29.
94503.
Okay. Millimoles of nickel. So now we're going to use this first chemical reaction. This is the amount of nickel that we had, and we want to know the amount of cyanide. So we're going to go millimoles of nickel to millimoles of cyanide. So we got millimoles of nickel in the denominator and millimoles of cyanide in the numerator. And we're doing all that so the units work out. And we get our ratio from the balanced chemical equation. There's 4 moles of cyanide for 1 mole of nickel, or 4 millimoles per 1 millimole. So we take that number times 4. (171801) millimoles of cyanide. And then what are we trying to do with that? We want the concentration, the molarity of cyanide in that original sample, which was 12.73 milliliters. I'm waffling here. Okay, I'm going to do it this way. So instead of stopping there, we want to go to the molarity. So we're going to divide by the volume. So we divide by 12.73. We get 0.0925382. That's millimoles per milliliter. But we can just cancel the m's out. And then we want to report this with the correct number of significant figures, and so it's 0.09254 molar. Any questions?
These are a lot more complicated.
Yeah, this is a lot more complicated than what you're trying to do on Friday, right? You should be able to do this, though. Now, should you be able to do it just like whip it out real fast? Not necessarily. It probably would have taken me a couple of minutes to sit down and do this. And I would definitely write everything out. This isn't something you can just take a couple numbers and be done with it. You need to learn how to write things out clearly so that if you come back to them later, you can see what you did. But more importantly, if you want to work in an analytical lab, somebody else needs to be able to see what you did, right? And so that's where writing things out with the chemical formulas and the labels with the units and everything. Now, a calculation like this, if you were doing a lot of different samples, the calculation might need to be done over and over again, right? So would you write all of this out by hand? No. You would write it out once, and then you would stick it into an Excel spreadsheet and let Excel do all the calculating for you. But you need to be able to show that it's true before you just start wildly calculating things. Make sense? This is an unfinished slide. So redox titrations, an example of that would be an oxalate and permanganate titration. Anything involving an oxidation reduction reaction. So the endpoint of that can be detected potentiometrically, but sometimes you can also use a redox indicator. Permanganate is great because it's self-indicating. Permanganate is intensely colored, and when you reduce it, I have to work through that in my head every single time. When you reduce it, it loses its color. And so that's pretty useful. But there are also some indicators, such as ferroin, which will change color when they're oxidized or reduced. And so you can put a little of that in your solution, and even though that's not your analyte or your titrant, it can tell you when you've reached your endpoint. So then I was going to talk a little bit more about that, but that's all I got. Auto titrators. So this is the perfect class to talk about auto titrators. So in an analytical chemistry lab, are you routinely doing titrations with glass burettes? No, you're not. Does a glass burette work? Doing it manually by hand? Absolutely it does. But there's some issues when it comes to an analytical chemistry lab. So an auto titrator, and this is just a picture of one that I pulled off the internet. There's lots of different kinds. You can get them for different kinds of titrations. You can get some that use spectrophotometry or potentiometry, all sorts of different detection techniques for finding that endpoint. And what most of them share is that they have some sort of automatic addition of your titrant. So advantages of auto titrators, the endpoint detection is based on data and not on opinion. So let's look at this picture. I'll just turn the lights up for a minute, don't be scared. So over here on the right, and I got these from Hanna Instruments website. Two samples, well, the same sample of milk. Here's its starting point at pH 6.8, and here is the end point of the titration at 8.2. Can you tell the difference? It's not real obvious, right? And if you have any color blindness issues, you might not be able to see any difference at all. 4 of my 5 boys have some issues with that. Over here are some graduated cylinders showing variations of that pale, pale pink that we're going for. So what one person detects as pink, another person might not see. So a disadvantage of the manual titration is that the detection of that color is going to depend on the individual doing the analysis. Seem to, the light people are not happy with me.
Was there a pH probe on the left-hand side of the back on the auto type, or here? The auto titrator on the left-hand, yeah, that
Here?
one, and then up, is that a pH probe on the?
You know, I am not even really sure. That does look like a pH probe right there. This is definitely a stirring plate. Here's the reservoir for the titrant. I'm not sure exactly what this is doing. There were so many of them, I just picked one that had decent resolution that wouldn't be all fuzzy when I stuck it up on the screen. And the prices vary widely. You know, some of them are, $20,000, $30,000, $40,000. But then you can get used ones for $400, So who knows what the quality is, right? Another advantage, though, is Time savings. If you have an analyst doing manual titrations, that requires their entire attention. You really can't do anything else while you're doing manual titrations. It also requires a certain amount of technical skill. You have to have experience doing it. So by using the auto titrator, the analyst can be doing other things while the machine is doing the really, really boring part, right? There are auto titrators that have auto samplers so that they can sample and titrate multiple samples. Those, of course, would cost more money. And there are others where you would prepare the sample, stick it in there, and start the machine. But then there's at least a couple of minutes while it does its thing that you could be attending to something else, preparing the next sample or whatever. So it can save time. You get better accuracy and reproducibility. On using a regular glass burette, you're adding a drop, which is 0.05 milliliters. And if you're good, you can maybe get half a drop and rinse it down the side. But some of these instruments can make additions as small as 0.001 milliliters. So that's what, 10 microliters? That's pretty small. So when your additions are that small, now we don't need 20 milliliters of titrant. We can use smaller volumes and still get the same precision. We can also then use smaller samples. And so that kind of gets into this next one, reduce titrant and sample usage, so that can save money, right? And you also have the issue of waste disposal, and effect on the environment. Another advantage to this is your accuracy, your reproducibility. It's not dependent on the analyst's skill. If you have the same person doing all the samples every day, day in and day out, maybe that's not an issue, but that's probably not going to be the case, right? You're probably going to be having a couple of different people working on something like that over the course of weeks or months. And this way, the results are going to be consistent regardless of who's operating the instrument. Another advantage is traceability. This instrument can be hooked up to a computer or even just a simple printer, and it will automatically print the result out. And so now there's a record of it that is a little more tangible than I wrote down these volumes that I saw on the burette, right? And so, trying to analyze samples and keep track of documentation to satisfy a client, they're going to like traceability, right? What?
It's like, oh, by the way, I'm colorblind.
So, John Dalton was colorblind. In fact, colorblindness was originally called Daltonism after him. So there's proof that you can be an excellent chemist and be colorblind. You do have some challenges when it comes to things like failing titrations, but it can certainly be done. So then another direction that I went from reading about all of this stuff, primary standards, right? There are all these different grades of chemicals. And I have been puzzled by this sometimes myself and had to go look something up. It's like, you guys need more methylene chloride or something. And it's like, well, you go back and there's like 3 different bottles and they're different kinds of methylene chloride. And it's important to use the right kind, right? So I just thought I'd share this with you. I got this information out of that tech handbook. So what's called commercial or technical grade, this is commonly used in industry, but generally would not be suitable for use in a chemistry lab because there are many impurities. It's good enough for the purpose that industry uses it for, but not good enough for the chemistry lab. The practical grade contains impurities, but usually it's good enough for organic preparations, but not analytical preparations. USP means it meets the standards prescribed by the U.S. Pharmacopoeia, so it's acceptable for drug use. So there the standards are ensuring that there's nothing in here that would be harmful to a person, right? This is going to be quite pure, generally acceptable for most lab purposes, but maybe not for good analytical work. CP stands for chemically pure. This is rather ambiguous, so the quality of that could vary. It's almost as good as the reagent grade, but what you plan to use it for will determine whether it's actually suitable or not. Spectroscopic grade, as the name suggests, is intended for use in spectroscopy. Here, we're concerned with purity in terms of the absorbance that it has, water that might be present in it, evaporation residues. So those are concerns that might not be of importance in another application, but for spectroscopy it is. So the principal requirement is that it has low background absorption. You don't want any contaminants in it that are going to cause background absorption. So this would be important in spectrophotometry in UV IR or near IR ranges, NMR spectrometry, fluorometry. And there's chromatography grade. So the minimum purity here is 99 plus mole%, and that's measured by gas chromatography. These reagents are accompanied by their own chromatogram for that batch, and it also indicates the column and the parameters that were used to test it. So this grade should have no individual impurity that exceeds 0.2%. Then we get the reagent analyzed or reagent grade. And this is typically what you'd use for chemical analysis. The American Chemical Society has a committee on analytical reagents. And they have a publication that specifies all the requirements for reagent grade chemicals. So if it's reagent analyzed or reagent grade, it meets those specifications. These bottles are going to be identified by a batch number so that they could be traced. Then we get to primary standard. There are, I'm guessing, probably most compounds could be prepared as reagent analyzed, but not everything can be made into a primary standard. These are sufficiently pure that they can be used as reference standards in analytical procedures. So you can use them directly by dissolving a certain massed amount in a solvent diluting to a known volume. These have extremely high requirements of purity, usually containing less than 0.05% impurities. I wanted to get a picture of this, but I didn't end up having time. When you look at the specifications that come with the reagent analyzed to the primary standard, it will give you what the manufacturer has analyzed as the percent purity. And so you can end up with something that's like 100.2% of your reagent. And that seems a little odd, doesn't it? How can you have more than 100%? Well, that would be a good thing. Or wait. Well, if you were doing something like calcium sulfate, if there were impurities that had a lower molar mass than calcium sulfate, you could find an amount of 102% or 100.2%. So if maybe there was a little bit of calcium hydroxide in there, calcium hydroxide is going to weigh less than the calcium sulfate. And so it's generally the presence of other compounds in there that have lower molar masses that are going to cause you to have that above 100%. So you don't want to go more than 0.05% below, but no more than 0.05% above either. Just general precautions that were listed. Some compounds form several different hydrates. And so you want to make sure that you check the formula carefully so that you're using the correct hydrate. That's one thing that just never fails to mess Chem 1A students up. Oxalic acid dihydrate. They just skip over the dihydrate thing and they calculate everything wrong. You may have a primary standard, but if the bottle has been opened, it's possible that that bottle has been contaminated. Also, your reagents can contain impurities that were not tested for. And so that's something to watch out for. What about trace analysis? So you guys have been analyzing a lot of water, right? Looking at very, very low concentrations of things. So down parts per million, parts per billion, this is trace analysis. So now the impurities in your reagent chemicals become really important. And you can also have issues with contamination of your glassware, right? So if you're analyzing chloride at trace levels and you're using flasks that the Chem 1A students use to make their super concentrated sodium chloride solutions, you may have washed that flask many, many times, but it's possible that there's enough chloride residue on that flask that it's going to equal or exceed what you're trying to analyze, right? So for the trace analysis, you have to be really, really careful. There are trace metal grade acids like nitric acid and hydrochloric acid that can be used to dissolve samples. You don't want to dissolve your sample and be introducing your analyte in the acid you use to dissolve the sample, right? And then this is some good practices for protecting your reagent purity. Because once that bottle gets opened, things can happen. And so we need to treat the bottle correctly so that it can be used again in the future. So when you are concerned about reagent purity, you should avoid putting a spatula into a bottle, even if you think the spatula is clean. The proper technique is to pour the chemical out of the bottle into a clean container and then weigh it out of that. When you're finished with that, you do not put that back into the original reagent bottle. Now, is this always critical? No, it isn't. Like, what was it the other day you guys were having trouble with? You were using the mallet?
It was the phenol.
Or the phenol fading?
Phenol? Phenol. So the phenol was caked up, and there's no way you could pour that nice crystalline out of there. That's not going to happen. It was jammed in there. So it depends on what you're using it for, right? If that was for trace metal analysis and you're using a metal spatula and hammering it in there, yeah, you're probably introducing some metal ions. For your purposes, it didn't matter, so it was absolutely fine. But that's the standard when you're working with very, very delicate things where you need real high accuracy. That's where those little weighing bottles come in handy. So you pour the chemical into the weighing bottle and you use the weighing bottle to measure out your substance. Of course, the weighing bottle has to be clean. Replace the cap on the bottle immediately to keep dust out. Dust has stuff in it, right? Dust is made out of chemicals. Dust falling into your reagent could have traces of that trace analyte that you're analyzing for, and it's going to mess everything up. And would you even notice? Not really, probably. And so that's one of the things that makes me crazy. Chem 1A, just ripping on them. I go over there, and there's like 3 reagent bottles with the lids off and spatulas sticking in them. I mean, that's just so wrong on so many levels. You put the cap back on. Some of those things are hygroscopic, and so they're going to absorb moisture from the air, and then they're going to cake up and get hard. And some of them, you know, you get dust or other things, impurities falling into them. Never put a glass stopper from a liquid reagent bottle down on the lab bench. I think we've all done that. Right? You should either hold it or place it in a clean place while you dispense the reagent. So the larger glass stoppers have like a flat, almost like a coin shape to them, right? A tab. And you can stick those between two of your fingers and still have the use of your hand. And so you can hold that stopper and you can deal with your reagent, and then you can stick the stopper back in the flask. And that's the proper thing to do. Because if you put it down on the bench, I tell my students that bench, you should think of that as being about as clean as a gas station restroom floor, right? So, you know, you've been in lecture and you're putting your hands all over everything, you know, and then you're going to eat a Twinkie or something? Would you do that if you'd been crawling around on the restroom floor? No way, right? Well, you know, you don't know what's on that bench. So you also don't want to be putting your stopper on there because it could get who knows what on it. It could also leave something behind that might be hazardous. And then we want to store chemicals in a cool, dark place and avoid exposure to sunlight. Some things are especially sensitive to light, and so those are stored in amber bottles, but all chemicals should be stored in a cool, dark place.